Hello everyone. I will be covering Swap Madness from the preliminary competition. So for this, as you could see, time limit is 1 second, and you have to determine the size of the largest swap free set. Now this is I'd say it's difficulty hard on this. It's not the easiest, and there's some stuff you're gonna need to know beforehand. So key points in the problem to get from this is that all words are unique. All words in the set have at least one letter, and every word is an anagram of every other word. So we have to know what an anagram is if you don't know. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all of the original letters exactly once. For example, the word binary can be changed to brainy and the word adobe into abode. So you just swap a letter or many letters. And I got it from Wikipedia, so you can look up elsewhere if you want to know more. And the background for this solution is first you need to know some data structures so you can implement the solution, such as queue, hash map, graphs, and all of these you can get from 302 or looking it up. And algorithms and concepts you need to know, which is the main part. For the solution, we need to know about bipartite graphs from discrete mathematics, Ford-Fulkerson algorithm for flow problems from CS 477, Ford-Fulkerson algorithm for the maximum flow problem, so you're just applying it to the maximum flow problem, and the parity of a permutation. So let me just make this bigger. So bipartite graph, it looks like this. We can get more information here. We do that. It's from graph theory. I won't cover it too much. Basically, you have these two graphs. You can do matches, like I won't cover it too much. The main part is we can match these nodes to another like set over here. Ford-Fulkerson algorithm for maximum flow problem. So I won't cover the flow problem or Ford-Fulkerson because I'm sure there's other people out there that could cover it a lot better than I can, and you learned it in 477. But this is a really good link, and I'll have it in the description. Basically, just a quick rundown is you see all these, this graph, you see these nodes, and these edges are like sending weight, or there's a certain flow they could pass through it, basically, like if you're sending oil through these like tunnels, basically. And basically, how much do you end up at the sink? Like, what's the maximum amount when you start the source? Goes from source 0 all the way over here. Well, the maximum is 23 in that one, because you can't really pass 20 over here, because based on what happens before, you can only pass 19. And 4 you could, so that's okay. So 4 plus 19 is 23. That's the maximum flow. And when that's gonna come useful, it's gonna be useful for us. And my solution, I basically just copied this, and you'll see that. Next, let's talk about the approach. Create a bipartite graph and match the words that are swappable. Perform maximum bipartite matching using Ford-Fulkerson's algorithm. The flow in the network is the number, and yes, we'll have two graphs, right, that we're gonna match to, like right here, like this would be the same as this. All the words in the set, like all these words. And we're going to match the ones that are swappable. We're going to have a source over here and a sink over here. So we're going to have 2 extra nodes on top of this. And yeah, the flow in the network that we're gonna figure out is the number of matched word pairs. Thus, the number of words n minus the flow is the largest swap-free set, and that's what we want to know. So that's the big picture view of the solution. And so we're going to have to use parity of a permutation, this concept in mathematics, so that we can figure out how to match the words correctly. So this is like this didn't show up well, but I have it over here. In mathematics, when X is a finite set with at least two elements, the permutations of X fall into two classes of equal size, the even permutations and the odd permutations. If any total ordering of X is fixed, the parity, oddness, or evenness of a permutation sigma of X can be defined as the parity of the number of inversions for sigma, i.e. the pairs of elements X, Y of X, such that X is less than Y and this function. So there's a lot to this, but we're gonna use that, and in code I could show you. Matching words that are swappable. Two words with the same parity cannot be swapped. So determining this is in code, it's fairly easily determined. A word will either be 0 or 1 parity, right? So right away, we don't need to consider two words with the same parity. We only need to consider when words that are different parity. Well, we're going to focus on either one. We pick 0 or 1, and then we figure out, because like this could be flipped the other way. So parity 0 words could be here, and we could do a flow and get the answer. Or parity 0 can be on this side, and parity 1 here. We do flow and we get the answer. So either way, it doesn't matter. So I just picked 0. Then with that parity chosen, set each word that can be 1 swapped to 1 to perform the maximum flow algorithm on. And final step, you use the algorithm and output n minus maximum flow. So going over this again, this is the solution. We're going to need to use this algorithm, which uses Ford-Fulkerson's, I believe. And for this maximum flow problem, like I was talking about. So since I know I have to use this, I literally just copied this whole thing right here, all of these functions. Or these two functions right here. And so we need m and n defined, which is, in this case, it's like the number of applicants and jobs, because that was like an approach that they were talking about for their problem. So that's why right here I say int n and m, and I change it later to be n. So that's where that comes from. And this, I just do a new definition for a graph, so I don't have to type that much. So it's a vector of vector ints. Okay, so this is literally just a copy right here of this. And I change it to work because this uses like a 2D Boolean array. I want to use vectors instead. So I had to change it up a little bit here. Just like how I pass it in. And I double checked the algorithms to see if it still worked. Here's parity. Well, I'll get to that. Let's go to main. So I get the size of the set, and then I set up the n and m so then it works for that algorithm that I copied and pasted. And then right here, I'm going to define words, vector strings, so I can get all the words in a vector. And that graph, I can, I'm going to initialize it, all zeros, n by n. And then I'm going to use a hash, the unordered map hash table for this word index that's located at. I read in the words, I see in each word And then I put it into the hash table. This a specific word, so string mapped to integer will be mapped to the index it's located. All right, so after that's done, I just do a length to hold the size of a word, and like this case it's 3. So right here we get the parity of the specific word that we're on, the first word, and so it runs this function. So let's go to that function. All right, so this is from Wikipedia. It's a number of inversions. As you can see, I just go and do this check. So I run this. It's basically n choose 2. So it's like this classic for loop. So I can go through every single one. And I check for the number of inversions. You can use a boolean and keep inverting it, but add it and then just do modulus. Either way, different words will have different parity anyway. The parity doesn't matter as long as each word that, like if parity is 1, we want it to be 1. If parity is 0, we want it to be 0. You know, we want to separate those sets. All right, so we select 1 or 0 like I was talking about. We're going to say 0 for now, or for this, it doesn't matter. And we're going to do another check here. This, so we can go through every single element of the set. And now we're going to perform that one swap and save it into a string. So using these indices that we make. So let's go to swap. Simply swap those indices and return the word. It's pretty simple. Right here, we're going to search if it exists, this swapped word. So we make the swapped word, and let's search the hash table if it exists. And then it gives us the index, because that's there if we find it. So we find it here. We go to the position of the graph of the eye, and then the index that we just found by looking it up. And then we set it equal to 1 so we can perform the algorithm on. And that's what we do for all of them. So we search every single word, do that, set a parity, and if it is like 0, for example, we do this. And this is, I did a function here, you know, just to print the graph, print these vectors. And this is the output for like test case 0, which is this one. This is how the graph would look like. And I just see out n minus calling this function. And as you can see over here, they declare this graph and then they call it the maximum number of applicants can get the job is this. So it just finds the flow, the maximum flow given a bipartite graph. And so that's the answer here. Let's copy it over. Let's run it. It passes the test cases. Let's submit it. And that's the answer. Thank you.